When you come inside from a long walk in the woods, or, after a few hours working in the garden, think about the very first thing you do.
You stop at the welcome mat.
Right, exactly. You vigorously scrape your boots. Or if you have kids, you're probably yelling at them not to track anything across the kitchen floor.
Oh, yeah, constantly.
We treat the ground beneath our feet with this really casual, almost automatic contempt. We sweep it away. We literally wipe it off our shoes. It is, in our minds, just dirt, like the least interesting, most mundane thing imaginable.
It really is. I mean, it's the ultimate linguistic symbol for something being worthless, right? We say an item is dirt cheap.
Yeah, true.
Or we just treat it as an annoyance, like a smudge on a clean floor. But that casual dismissal completely blinds us to this massive hidden reality. That smudge on your boot is actually a fragment of one of the most remarkable, complex, and desperately fragile systems on Earth.
And that is our mission for this deep dive. We are taking a stack of sources that detail the hidden, secret life of soil, and we're going to spend some quality time taking dirt very, very seriously.
Because we really need to.
We do, because nearly everything you have ever eaten, and almost all life on land, is built entirely on the mechanics of this one substance. Okay, let's unpack this. Because starting with the physical recipe of the ground, I always just assumed soil was essentially rocks that had been crushed into dust over millions of years.
Right. Well, finely crushed rock is the foundational starting point. But on its own, it's only a fraction of the story. I mean, if you just have crushed rock, you essentially have the sand on a beach or like the dust on the moon.
And nothing really grows in that.
Exactly. Soil is a highly specific, intricate mixture of 4 physical components. The first is that mineral matrix, so tiny grains of rock broken down over vast ages into sand, silt, and microscopic clay particles.
So that's the physical scaffolding.
Yeah, the scaffolding. But to actually make it soil, you need the second ingredient, which is organic matter.
Right, and in the reading, they use a very specific technical term for this organic component once it fully breaks down, which is humus, H-U-M-U-S.
Not to be confused with the dip for your pita chips.
Right, definitely not that. It's essentially the decayed remains of plants, animals, and microbes transformed into this dark, incredibly complex carbon structure. And reading about the chemistry of humus, it acts almost like a molecular magnet.
Yeah, it does.
It holds onto water and crucial nutrients so they don't just wash away when it rains.
That magnetic quality is vital. Humus carries a slight electrochemical charge, and that allows it to grab onto positively charged nutrients like calcium and potassium, and hold them in place for plant roots to access later.
Oh, that's why healthy soil has that deep, dark chocolate color.
That is exactly why. So you have the mineral scaffolding and the organic humus. The final 2 physical ingredients are actually empty space, meaning water and air.
The air requirement is what initially caught my attention, honestly. We tend to view the ground as this solid, impenetrable block.
Like a brick.
Yeah, but healthy soil is basically a sponge. It's packed with microscopic pores and channels. It needs those gaps because plant roots and living organisms require oxygen to fuel their metabolisms.
Right, they have to breathe.
And if you flood those pores with water and cut off the oxygen, the entire chemistry of the ground shifts.
The metabolic pathways completely change. When oxygen is cut off, the aerobic organisms, the ones that breathe oxygen, they literally suffocate.
Wow.
And then anaerobic bacteria take over, and their metabolic byproducts are often really toxic to plants.
Yeah.
The soil essentially turns into a suffocating, sticky mud.
So too much water is a disaster.
Yeah, but on the flip side, if you have air but no water, the biological engine grinds to a halt and you just get barren, blowing dust.
Okay, so we have the minerals, the humus, the water, and the air. That's the physical environment. But here's where it gets really interesting, because you can mix those 4 ingredients perfectly in a lab, and you still wouldn't have soil.
No, you just have a wet, dirty sponge.
Right. The 5th ingredient, the thing that actually makes the system work, is biology.
Yes. Soil is a teeming, breathing habitat, and the scale of that life is, honestly, difficult for the human brain to process.
The numbers in the sources were insane.
Right. A single teaspoon of healthy soil, so just picture a standard metal spoon from your kitchen. Cans contain billions of microorganisms.
Wait, billions? In 1 teaspoon?
Billions. There are more individual living things in that 1 spoonful than there are human beings on planet Earth.
That is just mind-blowing. And they aren't just sitting passively in the dark either. The sources detail this incredibly aggressive microscopic economy down there.
Oh, it's constantly churning.
The bacteria and fungi are the engine of nutrient cycling. They actually exude enzymes out of their own bodies to digest dead leaves and organic matter in the surrounding environment.
Breaking complex structures down into raw elemental forms.
Exactly, forms that new plants can actually absorb.
They are the ultimate recyclers. And you have larger architects, too, like earthworms, physically tunneling and eating their way through the earth, which, by the way, creates those crucial air and water pores we mentioned.
Ah, right, they build the sponge.
Yeah. But the fungal networks are where the biology operates on a level that feels almost like science fiction.
I want to focus on those fungal networks because the mechanics of how they operate are just astonishing. When most of us think of fungi, we just picture a mushroom on a lawn.
Sure, the classic toadstool.
But that's just the reproductive fruit. Beneath the surface, mycorrhizal fungi, which translates literally to fungus root, are spreading these incredibly fine microscopic threads called hyphae all through the ground.
Everywhere.
And they aren't just growing nearby. They physically penetrate the cellular walls of the plant roots.
They do. They form structures called arbuscules right inside the root cells. This creates a direct physical, biological interface between the plant and the fungus.
It functions like a subterranean barter system, or honestly, like a biological internet.
I like that analogy.
Because the plant is above ground, right, using sunlight to perform photosynthesis and manufacturing carbon-rich sugars. The fungus is underground, using its massive network of microscopic threads to mine the soil for water and vital minerals like phosphorus. And the fungus physically dissolves microscopic flecks of rock with specialized organic acids, extracts the minerals, pipes them back through the network, and trades them to the plant in exchange for those photosynthetic sugars.
What's fascinating here is that this symbiosis isn't some rare biological quirk. It is an ancient foundational partnership dating back hundreds of millions of years to when plants first colonized the land.
So it's the rule, not the exception.
Oh, absolutely. The vast majority of all plant life on Earth depends on this fungal internet to survive. A tree in a forest isn't an isolated pillar of wood. It is plugged into a vast subterranean grid that keeps it fed and watered.
Wow.
So when soil scientists say the ground is alive, they're stating a literal biological fact.
Which completely shifts how you view a patch of dirt. It's a bustling, invisible city down there. But, like any city, it isn't just a random pile of ingredients. The sources point out that this living system has a very distinct vertical architecture. It's highly structured.
If you were to dig a deep trench, say 10 feet straight down, you wouldn't just see a uniform brown blur. You would see distinct horizontal layers.
Scientists call these layers horizons, and reading those horizons is essentially reading the geological and biological history of that specific patch of Earth.
Let's trace that architecture from the surface down to the bedrock because I think it helps visualize it. Starting at the very top, you have the O horizon, which is just the organic surface layer, right?
Yeah, leaf litter, twigs, dead grass that hasn't fully decomposed yet.
And beneath that roof is the A horizon, commonly known as the topsoil. This is the crown jewel of the system. It is the richest, darkest, most metabolically active layer.
It's where all the magic happens.
Right. The topsoil is where the vast majority of that humus is concentrated and where those billions of microbes and fungal networks are conducting their trade.
The topsoil is doing the heavy lifting for terrestrial life. When we talk about global agriculture and feeding 8 billion people, we are entirely reliant on this one specific teeming layer. I keep picturing the Earth as this massive geological cake. And the topsoil is the frosting.
Oh, that's good.
It's an incredibly thin, sweet layer on the very top, holding almost all the life-giving properties.
And beneath that frosting, the environment changes dramatically. Below the topsoil, you hit the B horizon, or the subsoil.
The subsoil is usually much lighter in color because the organic carbon hasn't reached it. The reading describes it as an accumulation zone. As rainwater trickles down through the topsoil, it dissolves certain minerals and clays, dragging them downward until they settle and build up in this subsoil layer.
You will find deeper tree roots down there, seeking moisture during droughts, but the biological activity drops off significantly.
Like much quieter.
Exactly. And below the subsoil is the C horizon chunks of broken parent rock that are slowly fracturing. And finally, you hit the solid, unbroken bedrock from which the entire profile above was originally built.
So we have this vertical gradient, solid rock at the bottom, breaking down into chunks, giving way to the mineral-rich subsoil, and finally capped by that precious, dark, living topsoil. Which leads to a crucial question about the physics of how this architecture is actually built. We know we rely completely on this thin layer of topsoil. So how long does it take the Earth to manufacture it?
Well, the creation of soil is governed by two opposing forces, working in tandem at a glacial pace. The first force is weathering, which is the physical and chemical breakdown of rock working from the bottom up.
And weathering isn't just rocks banging against each other, it's a chemical attack.
It is.
Rainwater absorbs carbon dioxide as it falls through the atmosphere, creating a weak carbonic acid. When that slightly acidic rain seeps down into the bedrock, it slowly dissolves the silicate minerals.
Plus you have physical weathering, where water gets into microscopic cracks in the stone, freezes, expands, and literally shatters the rock from the inside.
So that's from the bottom.
Right, and simultaneously you have the top-down force, which is biology. Generations of plants growing, dying, and decomposing. Microbes and fungi processing that dead matter into humus. Earthworms pulling that organic material downward, mixing it with the freshly weathered minerals migrating up from the bedrock.
It's a slow-motion pincer movement. Bottom-up, chemical weathering, meeting top-down biological decay. So, factoring in that dual process, what is the actual timeline to build a brand new layer of topsoil?
Well, it varies wildly based on climate-like, heat and moisture accelerate the chemical and biological reactions, while cold and arid conditions slow them down. But on average, it takes hundreds to thousands of years to form just a few centimeters of fertile topsoil.
I'm looking at the timeline, thousands of years to build an inch or two of dirt, and I have to ask, if this system is so delicate and takes millennia to form, how on earth has modern industrial farming managed to feed billions of people for the last century?
It's a fair question.
We plow deeply, we spray chemicals, we disrupt that fungal architecture constantly. Shouldn't the entire system have collapsed by now?
We have managed to sustain those yields because we have essentially been mining the soil's historical reserves. We are drawing down the deep bank account of natural fertility built up over those thousands of years.
Oh, we're living on borrowed time.
Exactly. Furthermore, we mask the structural and biological decline by pumping massive amounts of synthetic nitrogen and phosphorus into the ground. We replace the biological engine with a chemical one. But the physical structure of the soil, the aggregates held together by the fungal glues and humus, continues to degrade under heavy plowing.
Which brings us to the mechanical reality of erosion. Because when you plow a field and leave it bare, or overgraze a pasture, you strip away the living net of plant roots that physically anchors the ground.
Without those roots holding the aggregates together, the soil becomes completely vulnerable to the sheer forces of wind and water. Wind can detach the dry particles and carry them as dust for hundreds of miles.
And rain.
Raindrops hit bare earth like tiny bombs, shattering the fragile soil aggregates and washing them into streams and rivers.
The terrifying part is the math. If it takes 1,000 years to build a few centimeters of topsoil, a single severe storm over a bare field can wash away millennia of the Earth's hard work in an afternoon.
If we connect this to the bigger picture, this is why soil erosion is a slow-motion global crisis. It doesn't generate breaking news alerts like a raging wildfire or a coastal hurricane.
Because it's invisible.
Right. A field losing a millimeter of topsoil a year to wind erosion is invisible to the naked eye. But globally, we're losing fertile soil exponentially faster than nature can replace it, slowly washing away our future food security.
To make this abstract threat concrete, the source material focuses on one specific case study, and that's Australia. The continent is presented as an extreme example of what happens when soil reaches its absolute limit.
Australian soils are uniquely vulnerable. They are some of the oldest, most heavily weathered, and fragile soils on the planet.
The text explains this by noting that the continent has been geologically quiet for an incredibly long time. In the northern hemisphere, or, along tectonic fault lines, the Earth periodically hits a reset button.
Glaciers and volcanoes.
Yeah, massive Ice Age glaciers acted like bulldozers, grinding down mountains and spreading fresh, mineral-rich rock powder across the continents. Or volcanoes erupt and spread nutrient-dense ash over the landscape.
Those geological events inject fresh, crushed rock into the system. It restarts the weathering clock and provides a new source of minerals for plants. Yeah. But most of the Australian landmass hasn't experienced massive glaciation or widespread volcanic renewal for immensely long geological periods. It sits on an ancient, stable craton.
It's just been sitting there, enduring the weather. For millions upon millions of years, the rain has fallen on the exact same dirt. The water has slowly dissolved the crucial minerals and leached them deep into the subsoil, completely out of reach of plant roots.
Just washed away.
Reading this, I kept picturing a tea bag. If you use the same tea bag to make a cup of tea every day for 1,000,000 years, eventually every single molecule of flavor and nutrients is going to be completely washed out.
The result of that million-year leaching process is that Australian soils are naturally incredibly thin and severely deficient in essential nutrients like phosphorus. For farmers operating in environments like that, the margin for error is essentially zero.
Because there's no backup.
Exactly. A bad storm washing away the topsoil is a catastrophe because there are no fresh minerals in the subsoil to tap into. It is just ancient, exhausted bedrock beneath.
So protecting the ground in those environments isn't an environmental afterthought. It is a matter of pure national survival. But let's shift the perspective away from farming for a moment. Suppose you live in an apartment in a massive city. You buy your food at the grocery store, and the agricultural supply chain feels very, very distant. Why is the health of the dirt still one of the most critical environmental stories of our time?
Because of the final massive mechanism we haven't discussed yet. Soil is one of the planet's primary carbon sinks.
Meaning it pulls carbon out of the atmosphere and locks it away. How exactly does it do that?
It goes back to that humification process we discussed earlier. All the dead leaves, decaying roots, and the billions of bodies of microscopic bacteria and fungi are carbon-based life forms.
Right.
When they die and are processed by the soil food web into humus, their carbon is locked into highly complex molecular structures that are resistant to further breakdown.
So instead of that organic matter rotting on the surface and releasing its carbon dioxide back into the air, it gets buried and sealed into the architecture of the ground.
The scale of this storage is monumental. The soils of the Earth hold more carbon than all of the world's plants, forests, and the entire atmosphere combined.
Let me make sure I'm wrapping my head around that. Every tree in the Amazon, every blade of grass, plus all the CO2 currently floating around causing the greenhouse effect, the dirt beneath our feet holds more carbon than all of that put together.
Significantly more. Which makes soil a massive double-edged sword. This raises an important question. How does our management of the ground dictate the future of the sky?
Because if we maintain healthy soils, if we keep the root systems intact, keep the fungal internet thriving, and allow the humus to build, that carbon stays safely locked in the vault.
But when we degrade the soil, the vault opens. When a plow rips through a field, it introduces a massive influx of oxygen into layers that were previously sealed off.
And that oxygen influx sparks a feeding frenzy, right?
Precisely. The aerobic bacteria go into overdrive. They consume that ancient stored organic carbon at an accelerated rate, and as a byproduct of their metabolism, they exhale vast quantities of carbon dioxide.
Oh, wow.
The carbon oxidizes and is released directly back into the atmosphere. Degrading the physical structure of the Earth literally fuels climate change.
So, what does this all mean? We started this deep dive thinking about a welcome mat, about scraping mud off our boots and cursing the dust on our floors. But looking at the sheer mechanical genius of this system, it's impossible to view a smudge of dirt the same way again.
It really is.
It is not just crushed rock. It is a biological internet trading resources in the dark. It is a fragile layer of living frosting that took millennia to bake, relying on complex chemistry and microbial economies to hold our food supply and the stability of our climate in a delicate balance. And it is a balance that can be washed away in a single afternoon. We want to thank you for joining us to appreciate the brilliant complexity of the ground beneath your feet.
It requires a complete paradigm shift in how we view the natural world. I'll leave you with one final thought to mull over, something that pushes the implications of this research even further.
I'd love to hear it.
We've explored how mycorrhizal fungi and plant roots are constantly exchanging resources, communicating, and cycling carbon across vast microscopic underground networks. The soil is teeming with trillions of organisms working in tight metabolic synchronization to regulate the Earth's chemistry and grow its plants.
Yeah.
Perhaps we shouldn't think of soil simply as a habitat where individual organisms happen to live.
What do you mean?
If this entire subterranean network is acting as a single coordinated system, how differently would we treat the ground if we viewed the surface of the Earth not as a collection of dirt and roots, but as one giant, interconnected living entity?